Welcome to our AI and Big Data in Finance webinar. We are delighted to have two distinguished speakers today. So we have Susan Athey from Stanford University, who will present her work on machine learning, who to nudge, causal versus predictive targeting in a field experiment on student financial aid renewal. Then Eckles from MIT will be the discussant. So Susan will have 30 minutes for the presentation. If there are any clarifying questions in the Q&A, I will briefly interrupt her after 50 minutes and ask the clarifying questions. Dean has 20 minutes for his discussion. Afterwards, we open the floor for questions from the audience. As an audience, please submit your question in the Q&A. I will then call on you during the questioning part. As a reminder, please be respectful with your comments. The presentation and discussion will be recorded and together with the slides posted on our website. After the main part of the webinar, we will have an unrecorded discussion where everyone in the audience will be upgraded to panelist. And without any further delay, Susan, the floor is yours.
Great. Thank you so much for having me here today. And I'm really delighted to get the chance to talk to this audience. And I'm also really grateful to Dean for coming to discuss. What I want to talk about today is really applying methods of machine learning to causal inference problems. And I'm going to use this a particular field experiment as a case study of that. But I will also highlight that Dean has done some great work and in some ways has some even better case studies. So you should, if he doesn't advertise himself, you should also check out some of his really nice work in this area too. So let me share my screen. The case study I'm going to talk about is joint work with Jan Spies and Neil Kelleher. But I'm going to start out by talking about the methods, which is joint with a couple of other co-authors as well.
That was very interesting.
So let me share the screen. I'm sorry, somebody's got some background noise. So I want to talk a little bit about methods as well as applications, and I wanted to kind of give a sense of the broader research agenda that I have been working on here. A lot of which is with the lab that I run at Stanford Business School, the Goal of Capital Social Impact Lab. So I put some links up here, and I can share them later as well. We have been working on both developing methods that can be used for things like personalization and designing experiments and social impact applications, as well as a variety of applications, including things like the financial aid nudge I'm going to talk about today. But we've also been running experiments with PayPal, trying to get people to give at checkout. We've been running experiments around misinformation and voter information and other settings. A lot of these experiments take a long time to go through and complete, so we will have more forthcoming as we go along. I also have a variety of tutorials and methods and R scripts, so please reach out to me for those if you're interested. So the big picture kind of theme through a lot of these approaches, or at least one strand of it around personalization and targeting and heterogeneous treatment effects, is that we're trying to get the right treatments to the right people, and that's really one of the big promises of machine learning. So, historically in social sciences, we had sort of intuition or theory-driven hypotheses about what works for whom, and we might test those. Now, even there, like in the experimental literature, the behavioral literature and so on, we typically have run experiments just hoping to get something that works for everybody. And you might pre-specify a few subgroups, but so there's relatively little applied literature that actually even attempts to figure out what works for whom and why. When I first started working on methods, I thought I would go back and reanalyze all these people's experiments, and I would just have a field day, finding and discovering all of this interesting stuff about, how, a treatment that was already shown to work well for everybody might work well for some groups and not for others. That type of research agenda turned out to not work so well, and we have some good intuition of why. generally, historically, when people have run experiments in social sciences, they are budget constrained and they have lots of interesting things to test. And so people tend to choose things to test that they think will work well for everybody. And certainly if you're not planning to do targeting later, if you test something that works well for some people and not for others, like you may not use it. And if you're planning to test averages, that thing might have an average effect of 0. So when you look back at a lot of the literature of what's been tested, it's actually hard to find things that people have tested that are really better for some than others. So one of the things I'm doing now in a lot of my active experimental design is trying to design more aggressive experiments to really try things that might work well for some people and not others. But I just want to kind of give that summary of, what we found in the previous literature. So generally, there's not that much of this, and there's a lot of room for creativity is my point, in even coming up with ideas of things that might work well for some groups and not for others. But the approaches, the methods that I spent some time building over the last 10 years are trying to build more data-driven approaches to discovering what works for whom and why. And I think here the idea is that, we really may not understand in advance all the things that could matter. We might have some pre-specified ideas, but there might be things that we don't know. And especially if we're thinking about doing experiments in a digital world where we might actually know a lot about people, there might be a lot of variables that kind of are proxies for other stuff. And so, we don't have a specific reason to understand why, say, somebody's history of shopping online is going to relate to which charities they donate. But we might discover such a relationship, and it might be useful for targeting, even though we didn't have a good theory in advance of why, or we wouldn't even know what their history is really proxying for. So the problem with data-driven approaches, like historically in experimental, was that, gosh, if you use the data to find subgroups, then of course you'll find something, but it'll likely be spurious. If a few people out there got high outcomes and they were in the treatment group, if I search hard enough, I can find some way to define a group that those people are in. And then I would spuriously find treatment effects. So if it looks like Markus had a really high outcome and Dean had a really high outcome, then I can define a subgroup around, brilliant social scientists and say they have high treatment effects, but that's not going to replicate. So a lot of the emphasis in developing machine learning methods for finding these subgroups has to do with not just bringing over great computational techniques that are good at discovering stuff with lots of covariates, but also to bring in to pay attention to our desire to avoid false discovery and to learn things that are generalizable. So that's been part of the attention in my methods work. So if you think about maybe a bit of a pipeline for understanding what you might do in terms of understanding heterogeneous treatment effects and estimating targeting policies, we can think of a pipeline where we first use some kind of machine learning method to estimate conditional average treatment effects. And my lab developed, and joined with Stefan and Julie Tibshirani, we've developed this methods with generalized random forest. And we have a popular software package that does that. And I'll talk a little bit more about that in a few minutes, but the big picture is that it's a software package that's designed to target treatment effects, and it's going to try to learn heterogeneity in treatment effects. But what's going to happen in a lot of cases, so the original theory there was really designed to kind of be able to do inference and come up with confidence intervals about heterogeneous treatment effects. But in practice, in smaller sample sizes, and especially if you've run or designed experiments, we often don't have enough data to really precisely estimate the full non-parametric treatment effect heterogeneity. Instead, these methods are going to be good at kind of telling apart the high treatment effects and the low treatment effects, but we can't directly trust the magnitudes of the models. The models it's too complex. We don't have enough data to really accurately estimate the full function. So in that kind of situation, which is really the most common situation, especially in designed experiments, is that you can use the data to create subgroups, based on the estimated treatment effects. And we have a theme, which I'll emphasize throughout, that you try to not use the same data to estimate the model and to evaluate the model. So we use things like cross-fitting, and I'll show you that. So we can create subgroups, and then we can say, okay, here are the people that our model has identified as having high treatment effects, and these are the people that have low treatment effects, and we can compare them. And that can tell us something about who has high treatment effects. And then finally, we can target treatment assignment policies based on these estimated treatment effects. And there we also want to be careful about taking the model too seriously. We don't want to necessarily trust our model. We want to evaluate our model in a sort of model-free way. And so in actually a bunch of different papers I've worked on, we've come up with creative ways to sort of evaluate the models using held out data to try to really assess whether they work and whether the policies we derive are good. Now, where you have to go see Dean, like I have a little bit of research MB, like my aspiration is always to do these policies and then actually go out and run another experiment and test them. You need a great partner relationship to do that, and you need to be able to like have multiple bites at the apple, and that's something Dean did. If you can find that type of setting, I think it's really exciting. There's also some work by Misra and Hitch that do that kind of running one experiment, estimating a policy, and then actually testing it. And that's very much on my research agenda as well. And we're working on those things, but I'm not going to be able to fully show you that today in my work. So now let me talk about a few of the methods and a few of the challenges. So first of all, I think probably a lot of people in this seminar are familiar with machine learning methods overall, and they understand that machine learning methods are basically, trying to use modern computational techniques to come up with good predictions. And a lot of the innovations in machine learning are sort of data-driven model selection along the path to predict well. And supervised learning allows you to kind of outsource the model selection to a robot. And the reason you can outsource that to a robot is because you can directly assess how well you're doing by looking at the mean squared error in a test set. So when I talk about AI broadly, I especially like, and I teach about to executives and stuff, I think that's like one great intuition to have is what's a good problem for machine learning and AI. It's one where you can define an objective, and it doesn't matter what the black box does. At the end, you can just assess your performance. And if your problem is to use X's to predict Y's, you can just hold out a test set and see if you did a good job. Now, there's all sorts of problems about stability, which I've also have a series of papers about stability of machine learning models, and there's other stuff to worry about there. But generally, at a first approximation, if you have a good mean squared error, you have a good model. Now, it turns out, actually, we were kind of surprised, even like within the class of forest models, which are old, but still a very good model. They're very popular because they work. We found that we were often able to improve the performance of even random forests by adding in some ideas from theory, including what we call honest estimation, where you don't use, it kind of protects against overfitting. So theory actually did help guide us to make better prediction models. But overall, that was great, but that may or may not have happened. In general, with prediction, you can just look at how well you did. Now, when we first started working on causal inference, and I've been, it's amazing how the time has flown. So I've been thinking about this since I worked on the search engine at Bing starting in the late 2000s, and then in the early 2010s, I started working on the theory here. And one of the first things that we confronted in thinking about applying machine learning to causal inference is that if you literally just take the problem off the shelf, you can't directly apply prediction methods to the problem of causal inference. And so the issue is, if we think of tau I as being an individual's treatment effect, that's never observed for any individual. So every individual in your test set has an outcome. So people have outcomes stamped on their forehead, but they don't have treatment effects stamped on their forehead. If I gave Dean a shot of coffee to keep him awake right now, I'm not really sure how I would compare the alertness of the actual Dean and the counterfactual Dean. And so I don't know the treatment effect of coffee on Dean. Now I can give coffee to a group of you, and then I can test the alertness of the group of you, treatment against control. But at the individual level, I can't. And so why is that important? Because, well, machine learning models are generally they're trying to get things right at the individual level. And so you want to target that. You want to see how well you matched up my individual treatment for Dean with Dean's actual treatment effect, but I'm not going to be able to directly observe that. So in one of our first entries to this literature with Hito, we kind of discussed this problem in this PNAS paper, and then we kind of went through possible solutions and talked about some of their advantages and disadvantages. So one thing you could do is you could just say, well, machine learning, if I want to learn about treatment effects, I can just take the treatment indicator, throw it into a big machine learning model, maybe it's a neural net or a random forest or whatever, and just let it go to town. And then at the end of the day, I can make predictions for the treatment group, make prediction for the control group, and see what happens. We use tree models to illustrate why that could be really bad, because if you have a tree model, it might not even split on the treatment indicator. So you might get identically 0 estimates of treatment effects for people just because you didn't happen to find that as the most important variable. And it turns out that's super important, because with experiments, often your treatments are not that important in predicting outcomes relative to other stuff. Like what the person did yesterday predicts what they did today a lot more than, the color of the ad or the behavioral intervention. So often you really need to tell the model that the treatment is what you care about in order to get it to focus on that. Otherwise it won't. So then, of course, if you want it to focus on things, another thing you can do is force on it. You can say, here's one model that's going to estimate outcomes for the treatment group, and I'm going to put one neural net for the treatment group and another neural net for the control group, and let's just take the difference. But the problem with that is that's also going to create spurious stuff. And again, tree models kind of really highlight that in spades, because what if you had one tree that split on male female for the treatment group? So maybe, male female was most important for the treatment group and young old was most important for the control group. And then when you try to use those two different models to estimate heterogeneous treatment effects, it's just going to automatically look like, men have different treatment effects than women, because you're actually comparing old men to, the average man. If you look at the predicted treatment effects for men, if you essentially are assuming by the model regularization that, gender doesn't matter for the control group and age doesn't matter for the treatment group, then you're going to just definitionally find treatment effects because you didn't actually compare apples to apples. It makes no sense, basically. So people forget about that because they think the machine learning models solve all problems. But in fact, in a moderate sized data set, these models are going to regularize. They're going to make choices. And there's just, even if two variables were equally important, just spuriously, one might focus more on one variable, one on another, and then you just get spurious results. So that's really a bad idea too. It's really important to actually just target the intervention, the treatment effect directly, and also make sure you compare apples to apples. So that's kind of been a theme of our GRF work, is that it's going to have this desirable apples to apples comparison, and it's going to use machine learning to optimize for the treatment effects. So really try to find treatment effect heterogeneity. So we propose a couple of other approaches. One is to estimate this infeasible loss. And we just point out that actually, this infeasible loss isn't as bad as it looks, because it depends on tau I squared, but comparing two models, the tau I squared just cancels out. It can't estimate it, but I don't need to estimate it to compare two models. And then what's left is actually objects that we can estimate. So we show how to do that in the PNAS paper. Another thing we propose in the PNAS paper is actually ways to transform the outcome so that each individual observation is a noisy estimate of the treatment effect, which seems very unintuitive. I'll have to refer you to the paper to see why that sounds like magic, but it's not. But if you're an econometrician or statistician, the idea is that anytime you estimate a parameter, each observation contributes in some way to that estimation. There's a score that contributes to it. And so we're using those scores as the left-hand side outcome. And that was also picked up by Victor Cherzanov and co-authors, and they provide more general theory for this. And then finally, a couple of other approaches, XLearner from a group at Berkeley and Our Learner by my co-author Stefan and me, and they basically come up with a way to optimize based on a residual regression. So the bottom line is there's a whole bunch of methods that have been at this point that you can choose from, but I think whichever one you choose, it's important that it's optimizing for the objective and that you're comparing apples to apples, and also that you use it in a way that you can trust your results. So just to give a little, I'm just going to really quickly go through the GRF. What we do in GRF is we basically use machine learning methods to create neighborhoods. So if I wanted to think about a non-parametric way to compare treatment and control, I can say, all right, Markus, he's a special guy. I want to find his treatment effect, and I want to say, well, who is it that's like Markus? Well, of course, nobody's like Markus. He's so unique. He's so awesome. But Dean's also wearing a blue shirt and is also a social scientist. So Dean is the best control guy. So I'm going to find the people who are close to Markus and estimate the treatment effects. But of course, there's so many dimensions on which to compare. Blue shirts and social science may not be the most important things. And if you have lots of dimensions, you end up comparing people who are pretty different, and you get pretty bad estimates. So the idea here is let's use machine learning to figure out which dimensions are important to create neighborhoods on, and then we'll create neighborhoods that way. And that's basically what we do. Now, matching says, I'm going to take just nearby people and ignore far away people. Instead, what we use is also to machine learning methods based on forests to basically create a kernel so that people who are I'm going to put more weight on people who are nearby in the sense of having similar treatment effects and less weight on people that are farther away. And I do that by averaging up different trees. So we built some nice theory about that. Again, we bring in honesty and subsampling, which create the first normality theory about and ability to construct confidence intervals with random forest. And then we go out and try to use them. So in our earlier papers, we used an application to general social survey. I want to show you this briefly because I want to show you the difference between like strong heterogeneity and then weak heterogeneity, which is actually what I find in the field experiment I'm highlighting today. So we reanalyzed the previous field experiment where we asked people, group A, are we spending too much on welfare? Group B was asked whether we were spending too much on assistance to the poor. Now, those are the same thing. This is just different wording. Okay, and it turned out it mattered how much how you worded it. We apply our GRF package to this data, and then we can look at the results of the estimated conditional average treatment effects. So this is just a histogram of the predictions, and it shows that for some people there was actually 0.5. So a big difference. This is 50 percentage points difference between whether you like welfare or whether you like assistance to the poor, while there are other subgroups based on their covariates that where this has a smaller effect. But these are just the model predictions. We actually don't know yet whether to take them seriously or not, because this is what the model says. The theory says as n goes to infinity, these are consistent estimates, but are they or are they not? So one of the things you can do is run a regression, basically, of the actuals on the predictions using the score approach. And what we find here, this is a calibration package that's based on some work for Viktor Chernozikov, and it's in our package. And we see here, there's a coefficient of 1.57, which basically is saying that roughly actually, it's not a perfect calibration would be 1, but the higher are our predictions, the higher are the actuals. And another way to see that more visually is that we use our estimates to put people into groups. And then within each group, we estimate the conditional average treatment effect for those groups. And the key point, and I won't go into the details now, but this is the big picture was really important, is that I'm going to use different data to assign observations to group and to evaluate their treatment effects. So for each observation, I'm going to use other parts of the sample to estimate their conditional average treatment effects and say, I think you're a high treatment effect guy. And then I'm going to come back and I'm going to then use completely untouched outcome data to evaluate, did I do a good job? And you see here, the slope is sort of close to 1 in the middle, but then we're actually not very good at telling apart the very high treatment effects from the medium high treatment effects. And so that tells us our model it's finding heterogeneity. And this is a model-free way to see, did we find heterogeneity? We didn't assume our conclusion, but we're not perfect. And we have a hard time telling the bigs from the highs. And we go through and we see, okay, it looks like political views are very important. Things like income can be important. in terms of understanding heterogeneous treatment effects. If we believe our model, then we can do things like look at partial effects. So we can say, holding everything else fixed, how different are conservative people versus liberal people in terms of estimated treatment effects? Or holding political views fixed, how important is income in terms of estimated treatment effects? And we see that both political views as well as income are important in understanding whether welfare is, sort of a stigmatized word relative to giving assistance to the poor. And we find that, for rich people or for conservative people, welfare is a stigmatized term. We also find that in these forests tend to kind of be flattened on the side, and we have another method called local linear forest that does some corrections for that, for boundary effects. Then we can also do things in 2 dimensions. So here we're showing like that being both rich and conservative gives you a nonlinear interaction effect for determining who is affected. So this is an example of a field experiment where there's really strong heterogeneity. Now let me go and apply these techniques to a field experiment that we were analyzing that has weaker effects, but still some treatment effect heterogeneity. I'm going to skip over this and then come back to that if there's time. So the field experiment we're focusing on was a collaboration with Ideas 42 and the City University of New York. And we're trying to understand here, how do you nudge people for financial aid, and how well the different approaches do in terms of targeting people for intervention. And so who should get a text message? And so one of the big ideas is going to be, we want to use these techniques I just showed you to figure out who has high treatment effects and who has low treatment effects, and try to target people based on estimated treatment effects. The text message experiment was run in 2017 and 2018. The control group got business as usual emails from the college, while the treatment group got supplementary behavioral emails and text messages. The sample was matriculated students from the City University of New York who had not yet renewed their financial aid forms in February of the study year. And the sample changes a little bit from year to year. We have 3 colleges in 2017 and 5 in 2018. And then overall, it turns out these text messages worked. So the on-time submission of your financial aid forms increased by 6.4 percentage points in 2017 and 12.1 in 2018, increasing the early filing rates from 37% to 43% in 2017, and from 38 to 50% in 2018. So this is this big picture that, like, a lot of consumers have trouble, doing what's good for their own financial health. And so behavioral nudges can actually be helpful in getting people to do this. And financial aid forms particularly are really onerous. And so this is a case where we might expect that this would matter. And so here's some examples of the text messages. You're getting texts that are kind of telling them what to do and reminding them and so on. So it's a series of reminders. So we then use the causal forest to estimate heterogeneous treatment effects. And the first thing we do is try to see whether our model is well calibrated. And I mentioned before, one way to do that is to construct these scores and use them as a left-hand side variable and see whether, like, the actual treatment effect is well explained by our estimated treatment effect. And so these slope estimates here, each of these rows are different regressions of, like, the actual on the estimated. And we see, and we would want them to be 1. We would like it to be the case that the estimated treatment effects well predict the actual treatment effects. And we reject that they're 0, which means our model isn't getting nonsense, but we also, they're pretty far away from 1, which says that our model is not well calibrated. And so even though in principle, in theory, with infinite data, our tau hat of X out of the causal forest should be an unbiased, a consistent estimate of the treatment effect for any X vector, and we should be able to build confidence intervals around it. These regressions are telling us, no, that's not a good idea. We don't expect our confidence intervals for any particular X to be centered on the truth. We don't have enough data. There's not enough power. So the easiest thing you could do with our generalized random forest is not going to be a good idea here. But we can still use the generalized random forest as an algorithm to put people into groups according to their treatment effects. And then we can still discriminate high from low, even if we don't have a consistent estimate of everybody's exact treatment effect from this method. So what we're going to do again is hold out one fold of data and then build a model on the remaining data and use that to derive a model mapping people to quartiles. And then once they're in a quartile, they've been assigned to a quartile using other people's data based on their X, but the mapping function was based on other people's data. So I build a mapping function, look at your X and put you into a group. And then I can look at the average treatment effect for people in that group. And their outcomes are clean at that point. So again, this is going to be model free. So what do we get? Well, we look in 2017 and 2018, and we see these are quartiles we put people in. And what's supposed to be the case is the high quartiles have high treatment effects and the low quartiles have low treatment effects. And it looks okay, but not great. So in 2017, we can sort of tell apart the people who had no effect from everybody else. And in 2018, we can kind of tell the top half from the bottom half. But we're bad at telling apart the third quartile from the fourth quartile. Like, it's just noise. We just can't tell the difference. So it's saying this model is okay for targeting, but not great. And we would have needed maybe different covariates or more data to really do a better job targeting. Then we try to look at this targeting and say, well, one thing that we could have done at the beginning is said we could just target people by their enrollment status. And so it turns out people unenroll in community college, people quit and come back all the time. So the fact that you're off working right now doesn't mean you're not going to come back next year. But we could have tried to just target people based on one covariate, their enrollment status. And if we look at that, we see that actually, if we had known in advance that that was the thing that was most important, we could have done a better job with the pre-specified groups of targeting by enrollment if we knew that. And we knew their enrollment status than if we used our model. So this is kind of also showing that machine learning kind of has a bit of a cost in that if you use the data to try to discover something, you're doing sample splitting, you're trying lots of things, you might make mistakes. And so actually, if you had this data and you knew what you were doing, then that would have been better than our machine learning based approach, at least more so in 2018 than in 2017. And to make this apples to apples, we have the same number of people in each group. So there were 27% unenrolled. So we compare that to the bottom 27% using our machine learning model. And we just see we get more separation between the groups from this one variable than we do from our machine learning model. But again, in advance, we wouldn't have necessarily known that was important. And if we were trying to test every subgroup, then we might want to do multiple hypothesis testing, correction, and other stuff to look at this. So we've kind of cherry picked the best result and compared that. Then the really kind of main focus of our results from the paper is summarized in this picture. So it's a pretty complicated picture. So let me try to talk through what we're trying to show here. What we're trying to do in this picture is look at the different types of targeting approach and summarize all in one picture how well different targeting approaches do. So the x-axis has the percent treated, and the y-axis has an estimate of the overall enrollment you get when you use a specific targeting policy. So the easiest one to understand is this pink line. And so this is saying the pink line is showing like a point on the pink line, say the point corresponding to 50% treated, says, what does our model say that, or what do our estimates say that the filing of forms would be if 50% were treated? And that says it's somewhere around 0.4 would do their filing. And it's a 45-degree line, because if I'm randomly assigning people, then just giving more people to the treatment is going to give you the same effect no matter how many we do, because I'm randomly selecting the people. So it doesn't matter, which percent I'm doing. Now, we have some other things, which, like, say this blue line is the inverse baseline. So here we built a predictive model and said, I'm going to predict the people who we're already going to fill out the financial aid form without the intervention. And then I take the inverse of, then I take the, we're calling it inverse baseline because we might have thought that the people who you most needed to nudge were the people who weren't going to fill out the form. But it turns out that in this case, the people who were going to fill out the form are the people for whom the nudge is most effective, which might seem counterintuitive at first. And it turns out that that policy looks good. That is, if say I took the 50% of the people who were most likely to fill out the form without the nudge, and then I nudge those people, I get the highest benefit from giving that 50% of the people. Whereas our Kate is this green line. So the green line is above the pink line. So it looks like better than random. If I wanted to say target 60% of the people, that green line is above the pink line. And it says, targeting 60% of the people with Kate is better than randomly targeting them. It's certainly better than targeting the people we predicted were not going to fill out the financial aid forms, which is this bottom line. But it's not as good as targeting the people who were going to fill out the financial aid forms in advance. So if you knew what kind of predictive model you wanted in advance, which you wouldn't necessarily have known, then the predictive model actually looks good, but we have to predict who was already going to fill it out. And it's like we're nudging them over the finish line. But we needed the Kate model, and the Kate model, it turns out, wasn't any better than that, but we didn't know that without testing it. And so the general theme is that overall, you would like to target the people for whom the estimated treatment effects are highest, but how important that is and how well it works relative to some prediction model depends on what you were predicting. Like you could go really badly or really well predicting stuff. And it also depends on just how good you are at estimating treatment effects. And we're sort of medium good in this particular field experiment, but not great. So if I was designing a future experiment, I might think about collecting different covariates, and I might also think about treatment assignments that are specifically targeted, say, at people who weren't going to fill out the forms anyways, or better ones that are really good for people who were going to fill out the forms anyways, once I understand the different groups. So that would be like a future field experiment that would make advantage of this work. All right, so let me stop here and I will turn it over to Dean for discussing.
Great. Yeah, very, very interesting. And obviously there's a lot to comment on here. So I'm going to kind of take a particular view of this. So this is very interesting work. And I think hopefully gives a good sense of, I guess, what the state of the art is here, what's possible and what some of the challenges are. So let me go ahead and share my screen. Okay, great. So I'm Dean Eckles. I'm at MIT, and I kind of split a lot of my time between working more as a methodologist and then actually doing more social science work myself, running a lot of field experiments and analyzing them. And so that's kind of the perspective that I'm coming at this from, and I'll try to emphasize some of the practical challenges of all of this. So anyway, I think this is an interesting paper. I think overall the picture is that there's analysis of some large field experiments, a couple of them, and there's actually a replication I wrote 2019, I think it's supposed to be 2018, but there's two different large, well-powered field experiments. This seems like the perfect basis for looking at, are there heterogeneous treatment effects of the interventions that are studied in those field experiments? Then they use causal force, one of the nice approaches for doing this, to estimate treatment effects there, and are pretty forthright about some of the challenges of doing so. And then consider how you might actually use those heterogeneous treatment effects to do targeting. So what I was going to say a little bit about is just some of the challenges of estimating heterogeneous treatment effects. How learning a targeting policy is different than learning those heterogeneous treatment effects. Some intuitions that we might have about what heterogeneous treatment effects look like, and how this all might inform us in designing experiments as well. So first, learning heterogeneous treatment effects is hard, right? I mean, one of the big things that's featured in a lot of social science, experimental social science, is that so much of it has been underpowered, that the experiments that people run a lot of the time just sort of barely have enough signal to detect anything that is going on. So even in the case where we have well-powered field experiments, which we do here, the z-stats for the average treatment effects of this text message nudge on people submitting their FAFSA forms is over 10. So we're really well-powered for the average treatment effects, but things can get a lot harder for heterogeneous treatment effects because effectively you start trying to divide this large sample up into a lot of pieces. And often when we have these large sample sizes, we may also have the sort of benefit or curse of having high dimensional covariates. So this becomes quite a challenge where a lot of these asymptotic approximations, which are great to have, may provide limited guidance for the challenges that we face when actually trying to estimate these conditional average treatment effects. Now, some of this paper is focused a bit on what I think of as a more practical problem that has some different characteristics and maybe avoids focusing on exactly how well we've estimated the heterogeneous treatment effects. And so, when we're learning heterogeneous treatment effects and just saying we're estimating these conditional average treatment effects, the focus is often on the point estimates. And then we try to decide, hey, are these point estimates good by looking at some loss function that we use for, continuous predictions, like a mean squared error. And then maybe hopefully other measures of fit. And actually, I really like that this paper looks at questions of calibration. So of course, in some kind of narrow theoretical sense, like statistical decision theory, right, we could say that these point estimates are a decision, and we have this loss function for our decisions. But what are we ever really deciding based on a whole bunch of estimates of heterogeneous treatment effects? What's kind of the point of doing that? And I think there are some good answers to that. One may be that this is informing some theory, right? That our theory makes predictions about who the treatment effects should be large for and who they should be small for, or that our theory says that they should be sort of uniformly positive for anyone. And that might be a practical issue as well. We, as Susan started by talking about, in the absence of being able to target, we may really be looking for interventions that have uniformly positive effects, right? So there are some decisions you might make based on them, but learning a policy or a decision rule for assigning units to treatments is kind of a much more practical and immediately applicable question in a lot of ways that also just sort of has some different characteristics from a statistical perspective. It's essentially a classification problem, right? If our actions are discrete, we're deciding which units we're going to assign to these different treatments. Say in the binary case, are we putting them in treatment or are we putting them in control? And our loss from misclassifying somebody depends on their true treatment effects. So if somebody has a positive treatment effect, right, and we put them in control, then we lose whatever that treatment effect was by putting them in control. If they should have been in control, but they got put in treatment, then our treatment loss is actually their negative treatment effect, right? So, that's how we can kind of think about what we're doing when we're learning these treatment policies. And just a little bit more formally, right, that these policies, like a policy pi, is a mapping from this space of covariates to the actions, or possibly the probability distribution over the set of actions. So the simplex of, maybe there's 5 different actions we could take. And so our goal is to try to somehow maximize, maybe if we've set up the outcomes to be something we're trying to increase, to maximize the expected outcomes under this possible mapping from the covariates to the outcomes. And so that's sort of the problem that then we're facing in this targeting case. It's a bit different than just estimating heterogeneous treatment effects, when it's a bit different than prediction. And so there's just some interesting conceptual things about that. One that I think is it forms the basis of what Susan and co-authors do here is that from a single experiment, we can evaluate many targeting policies and compare among a bunch of different targeting policies, even if we haven't specified those policies in advance. In order to do that, if we have a randomized experiment, right, we're going to look at those units where it just happened that unit was assigned to treatment and the policy said to treat them, or that unit was assigned to control and the policy said to put them in the control. Right. And so to evaluate any policy, we can just look at those matching cases where, because of random chance in our randomized experiment, we did what this policy of interest would have done. And then actually, when we're making contrasts between policies, we're going to look at cases where those two policies disagree. So a lot of times two targeting policies might agree on a whole bunch of units. So here, policy 1 and policy 2 agree on all these units and all these units, but then they disagree on some units that maybe should be treated under one policy and not treated under another policy. And so, when we're thinking about what the challenge is of comparing two policies, it's going to be in contrasting those cases where the policies disagree. So just to give you another example of this kind of thing, here's some work by some of my colleagues here at MIT, where they were targeting some promotional discounts. And they ran a field experiment where they just randomized whether people got discount A, discount B, or the third option, which was a control. Okay, and then they did a bunch of procedures along the lines of exactly some of the options that Susan has described, and but they used a lasso instead of forests in this particular case to try to figure out how to assign people to one of these three actions. Now, here we're comparing basically the profits in different subgroups that are divided up by the treatment that's recommended by the lasso policy, right? And comparing it, comparing the outcomes under the lasso policy with what if we just take action A all the time? Well, in the group that the lasso says to take action A, and also the uniform policy says to take action A, then these two outcomes should match except for sampling error. So essentially, when we're comparing policies, right, in the cases where they agree, this is irrelevant to the comparison of the policies, right? What we're zooming in on is the case where, if we were doing, this uniform action A, and the lasso says to do something else, those are the cases that we end up zooming in on, right? And so it's potentially all of these cases, and we might see some evidence in particular that when the lasso says to take the control action, that this other policy is saying to, uniformly give everyone discount A, and that's worse off than if you do whatever the lasso says to do, which is here to leave that person in control. Okay, so I think that's kind of an interesting, just conceptually feature of the problem of learning optimal targeting policies and comparing them is the way that we can do it from existing field experiments, and how when we're comparing two policies, we're effectively, even if we don't do this, we're zooming in on the cases where they disagree. Okay, so so that's kind of the basic problem that appears here. One of the things I wanted to pause and think about is what we expect to gain from a targeting policy in this case. And Susan led off by saying that a lot of things that people have tried before is things that they think won't backfire for anybody, right? So in this paper, one of the results is that there aren't really subgroups where there are negative effects. Turns out sending people text messages reminding them to complete their FAFSA forms doesn't really cause anyone to say, screw you, I'm not completing my FAFSA forms, even though I was planning to already, right? So that's nice, right? That's a nice feature to have, but it means that in some ways, what we can gain from targeting here is a little bit more limited, right? Only if we're facing some sort of budget constraint where there's some cost of sending these text messages and our budget is smaller than the total cost of sending everyone those text messages, would we want to adopt a targeting policy that basically isn't just treating everyone, right? So I think that's an interesting case, right? When we do have these sorts of budget constraints, then we do want to somehow rank people by the gain we get from treating them and treat people in that order up until we reach the budget constraint. And there's actually some really interesting recent work by Susan's colleague and frequent co-author Stefan where they're basically, they don't say in the paper what they're really doing, but I kind of guess that they're targeting these kinds of promotional discounts for things like Uber Eats or Uber Pass. And actually in those cases, the costs are heterogeneous as well and not known in advance, right? With sending text messages for FAFSA, maybe the fee that you're charged by the company that's sending these text messages for you is uniform, right? Whereas here, the costs that you're incurring by basically making drivers whole or restaurants whole when you give somebody this discount is heterogeneous depending on how much people use it. So, so to me, I was kind of thinking, do we have budget constraints in this FAFSA setting? If we don't, can we just treat everyone? And maybe part of the bigger message here is that given that we have this technology, right, this ability to do this kind of scalable targeting, maybe we ought to try a wider range of messages, right? And so here, if it was not treatment versus control, we had a bunch of different messages. The choice might not be, do we send the message or not? It's which of the many messages do we send? So, and I think we're kind of, you know, in agreement on that point. So I just wanted to kind of wrap up by saying some things about vague intuitions about heterogeneous treatment effects. So why would they have different distributions? So say our outcome Y is a binary choice, okay? So if treatment increases the utility of taking that choice, or expected utility you get from making that choice, then it seems like effects should be largest for people who have a baseline expected utility near zero, if people are rational utility maximizers. So if we think that, you know, there's you know, people who you know, are going to have a larger treatment effect if their baseline utility is near zero, and maybe the baseline utilities are distributed like this, right? And here's zero. Then the biggest effects are going to be for these people who are near zero, and maybe we get kind of you know, a smooth distribution of treatment effects, and there shouldn't really be any treatment effects that are negative, right? So that's kind of one theory of heterogeneous treatment effects, right? Another theory of heterogeneous treatment effects that is basically falsified in this case is if the treatment works for the same fraction of all people, any type of person, it, you know, has a 10% chance of working on them, but it can't get people who are already taking the action, that is submitting their FAFSA forms to take it, then effects should be largest for groups that have a small probability of taking the action. That seems to be falsified here, right? And actually that seems to be falsified in a bunch of other settings related to churn management. You might think you should target discounts at people who are possibly going to churn, because the discounts can't keep the people who aren't going to churn from churning. But that turns out in a bunch of cases, you know, for example, here's one from a paper by Eva Escarza, that doesn't work out, right? So whereas in other cases it may work out. In some of my own work that turned out to work out. So anyway, I think it's useful to think about what our theory of these heterogeneous treatment effects is, you know, and when we might anticipate negative effects. Do we have substantial costs from this? In which case, you know, we may be caring not about this point 0, but some other point C, and we might imagine that then there's a lot more people with substantially negative treatment effects once we account for our costs. So overall, I just want to say I think this is really really interesting example of applying some of this, you know, the state of the art here. And I would have loved to comment more, but I think I'll stop right here. Thanks for sharing this interesting work.
Thank you so much for this great discussion. Susan, would you like to respond to Dean's comments? And while you're doing this, we can collect more questions from the audience that I can ask next.
Great. Yes. So, and I just put into the chat, I noticed I had an error in my slide with an outdated link. So I put in the chat, if anybody's interested, the link to tutorials that are that show how to do all this stuff. So I agree with everything that Dean said. And in fact, like I think he basically he said a lot of things that I would have said that I cut out of my talk more articulately and deeply. So thank you for that, Dean. That was awesome. Just a few specific points. First, I think one big thing that Dean emphasized at the beginning, which I just want to highlight, is that I think people think at the beginning that estimating a targeted treatment assignment policy is sort of harder than estimating heterogeneous treatment effects. Because in the first you do the treatment effects, and then there must be some other really hard thing you do to get a targeted policy. But in fact, estimating a policy is a lot of ways easier, because even if the function mapping X's to treatment assignments is complicated, in the end, you're putting people into groups. And then evaluating and understanding what happens in groups is just taking averages if you have experimental data. It's an easier problem. And then just as Dean said, then things, in addition, if you're comparing two policies, you just have to focus in on the places where they're different. And so, So when designing and planning and evaluating and intuiting about experiments, really the first thing you need, or about policies, the first thing you need to do is just say, well, gosh, do I think there's some group out there where where they should get different things? And if I want to think about whether my experiment is powered for that, I'd say, well, if I think there's some group, maybe roughly it's like old rich people or something. Think, how many old rich people do I have? And is that enough data to tell the difference between, arm A and arm B? And roughly, if it's not, you're not going to be able to tell the difference between the two policies. So, it's easier than you think to reason about learning targeted treatment assignment policies. Something that Dean kind of hinted at that I didn't have time to elaborate on is, yes, there's also if your ultimate goal is to estimate a policy, you do the optimization a little bit differently. And we do have software that's directly designed to optimize for that, called Policy Tree. So we have a, and it's, I would say that problem has good theory. I've written some theory, other people have written some theory, but I don't think the problem is completely solved though. Like, what's the very best way to optimize policies? A few other comments that he made that I think is really interesting is that, yeah, who is it that's most affected? Just as Dean said, like, you might think that if there's a group that's already doing something, like, there's just no room to get bigger treatment effects. But there actually are a bunch of applications now we're finding that actually that still is the group that you want to nudge. And we also see that a little bit in my charitable giving work as well, which I haven't quite finished yet. And so I guess the way I think about it, there's some scenarios where there's people who are like paying attention, or like who, for even this is even relevant. And in some cases, the thing you're able to find with your X's is those people. And if there's a bunch of people who this is just not relevant, they're not paying attention at all, they're just going to drop out of college forever, or, they're never going to donate to charity, then those people are like big fat zeros. So, and so in some cases, the best thing your model is able to do is just find the zeros and focus on the others. While in other cases, there's something richer going on. And so it sort of depends on the setting, like which one of these things is happening. Then the final point Dee made that, this is not like the perfect application, because it is like the actual intervention we tested, like text messages, they're not that expensive in the US, and you could just send more. Now, there's a broader context, though, where the university might be texting you about other things, and there's an opportunity cost of the attention. So implicitly, there may be a cost. But, one of the things we ideally had in mind is if we can figure out the people for whom text messages, generic text messages work, we might be able to actually target even more expensive interventions, like two-way messaging with a real human, or, calls or other stuff. So this also was like a step on the path to maybe more expensive interventions. And then in general, if you're going to blast out text messages to the whole country or something, like, they do cost something, like, you have to pay to do this. So if you were going to expand the FOSFA nudges beyond, this context, they would be expensive. But it's not like a perfect fit where we've exactly solving the specific problem for this specific nudge. So I agree with Dean on that criticism. It's completely, it's fair.
But I think this point about keeping that channel informational and not noisy is an important one. In some of my other work, we've run some large field experiments with a fitness tracker app, where you get notifications when your friends are running, and you want to somehow rate limit that, so that you send them a bunch of notifications that are potentially persuasive and keeping them running and keeping them engaged with the app, but you don't want to send too many. And we, in fact, in our field experiment, find an interior solution in terms of how many of those you should send. So I think that is a good point that applies here, is that this is not a channel that you want to just, burn this bridge in order to get them to apply for FAFSA at all costs, right?
Great, but thanks for those brilliant comments, and it's really a pleasure to talk about this with Dean, who, as I mentioned, is doing some of the most exciting work in this area too.
Thank you so much. We have a number of questions in the Q&A, so I've made all of them public so everyone can see them. Given that we are moving towards the end, I would suggest that we go over those questions in the 50 minutes of the non-recorded part of the session. So I will now announce the next seminar. Let me first give our speaker and discussant a big round of applause. And that is where we should hear virtual applause, actually. Okay, I will just give we will have our next ABFR webinar on September 30th in 1 month. And we have a very exciting lineup of future speakers, including Jiang, Eric Brynjolfsson, and Gerald Hoberg. So you will see more details on our website, so please stay tuned. We are now upgrading everyone to a panelist, and we'll then go over the remaining questions. So please stay in this room if you would like to be part of our unofficial discussion part. Thanks again for everyone joining us today.